So our next part of the review is tangent and normal lines. So I'm going to find the tangent and normal lines to e to the 5x squared plus 2 at x equals 5. Excuse me. I wanted to pick a somewhat challenging one so that we could also, work on, well, and also it's like this is sort of what the quiz is going to entail too, is something like that. All right, so what we need in order to do this is we need to know what f of a and f prime of a are, and a is equal to 5. So this is our a. All right, so in order to do that, we need to know f prime. So this is our f of x is equal to e to the 5x squared plus 2. Then f prime of x. Well, we have a function inside another function. This 5x squared plus 2 is really inside the e to the x function. So that means that we have to do a chain rule. So we're going to do derivative of the outside function. Derivative of e to the x is e to the x. So that e to the 5x squared plus 2 is going to stay e to the 5x squared plus 2. And then I have to go times the derivative of the inside function. So that's what we usually call g prime, right? So we're going to go times g prime. So that's going to be 10x. All right. Now, I could probably just leave f prime like that if I want it. And then f prime of 5. So we're doing it at x equals 5. So it looks to me like we're going to end up with some huge numbers here, but that's okay. We got calculators, no biggie. I have e to the, so 5 times 5 squared is 125 plus 2 is 127. E to the 127th power, that's a huge, huge number. All right, but that's okay. Again, we have calculators. And then I'm going to be times 50, so it's equal to 50 e to the 127th power. All right, so then I'm ready to write, I guess I need to know what f of 5 is as well. So f of 5 is, I just put 5 into the original function. So it's e to the 127 plus 2. Oh, just e to the 127. So I put 5 in for here. I'm going to get just e to the 127. All right, so then I can write the equation of the tangent. It is going to be y minus e to the 127 equals 50 e to the 127 times x minus 5, okay? So the f of 5 is going here, the f prime of 5 is going here, and a equals 5 is going here, right? This is f prime of 5, this is f of 5. All right, and then what I'll also do is before I do even think about simplifying this, which by the way I don't have to, I will write the normal right away. Now I need to indicate that this one's the tangent. So I need to indicate which one's the tangent, which one's the normal. And then for the normal, I just write the exact same thing, except that I take the negative reciprocal of this, so it's going to be negative 1 over 50 e to the 127th times x minus 5, right? And I can just leave them both like that. So that's it, done. All right. Now, if you want, you can check these, and one of the nice things is a lot of ways to verify, graphically what we're seeing here as our result and make sure it's right. Because if I graph it and it looks wrong, then it is wrong. All right. So it's easy enough to solve this for y. All I have to do is put the e to the 127 on the other side. So we'll see how well Desmos handles these huge numbers, because they're going to be huge, and we're going to have to zoom out like a lot. In Desmos, under functions, I think it's under miscellaneous, you have a function called exp, right there, exp. That's e to the x, is the exp under miscellaneous functions. So e to the power of 127. So this is how you write e to the 127th power in Desmos, is 50e to the 127th. You do 50 exp 127. Notice it's already telling you that that's 7.15 times 10 to the 56th power. So since you understand scientific notation, you know how enormous a number that is. Okay, and then I'm going to do the x minus 5, so times x minus 5. But then I have to bring the e to the 127 over there. So I'm going to go plus functions exponent 127. All right, so I have that's just my equation of my tangent. So what I forgot to do is write in the actual function, which is e to the 5x squared plus 2. So that is going to be functions exponent 5x squared plus 2, 5x squared plus 2. All right. Now, so my graph doesn't look like much, so I know I have huge, huge numbers, so I need to zoom in like a lot this direction, and I can see the graph's getting pretty interesting. It's sort of really flat on the bottom. My tangent is super vertical, but see, I've got only 10 to the 11th here. I know I need 10 to the 56th power, so, you know, it's going to take a lot of zooming. I don't know how well your calculator would even be able to do this. I'm up to 10 to the 24th power. I need 10 to the 56th to even be close. But I'm also seeing that, like, this is a pretty weird example of a tangent because everything's so vertical, because this graph is so huge. It's pretty interesting, though, if you think about it. Like, basically, if I, zoomed out. If I have a number between 0 and 5, the value, the y value is almost 0. And otherwise, it's like infinity-ish. All right, so I can start to see, you know, there's where it's the tangent. So it's kind of interesting. So it sort of looks a little bit sort of, you know, we look at this and it looks sort of intimidatingly weird. But all you have to do is sort of zoom around and we can start to see that, I wonder if this works. If we can start to see that point of tangency where it really looks tangent. Yeah, I can see it. I'm trying to do like a zoom where I can zoom on just that axis, but it's hard to do because of we have to go over to the actual axis. All right, I'm going to stop doing it. Because, all right, we can see that that's tangent. You know, I could just do like a big zoom out on it, and you can see that the line is tangent to the curve. But notice how you had to do like an immense amount of zooming around to do that because these numbers are so enormous. But, you know, you have computational devices, they can handle those huge numbers. All right. Now, if we wanted to do if I do the normal line, because my axes are scaled so radically differently at this point, it's not going to look vertical at all. So I'm not going to bother with that one. Check the tangent, and then, you know, the progress from the normal to the tangent is pretty easy. You just do your opposite reciprocal of the slope, and that's it. All right, so there you go. There's a tangent and normal of a pretty weird example.